Traditional neural applications or brain-computer interfaces using electroencephalography or magnetoencephalography implicitly or explicitly rely on three elements. Firstly, they require the user to follow specific instructions. They are active, necessitating a high concentration from participants or users. Secondly, they operate on controlled synthetic stimuli, such as beep sounds or flickering patterns, to elicit controllable brain responses. And thirdly, these synthetic stimuli need to be repeated multiple times to average out the noise. In the last few years, there has been a shift from these traditional BCIs towards more naturalistic brain-computer interfaces that are passive, not requiring any specific participation or instruction from the user, and that are single trial, and moreover, use natural stimuli, such as speech or video footage. And this enables various new applications, for example, in hearing aids, in virtual reality environments, the online classroom, or neural marketing. However, this shift entails several fundamental signal processing related challenges, such as the strong subject specificity of the brain responses. Due to using these uncontrollable natural stimuli, there is also a much higher variability in the neural responses, but especially the low signal-to-noise ratio of the neural signals of interest. For example, the stimulus following neural responses. They are buried under all kinds of different physiological and non-physiological noise sources in the EEG. One especially powerful tool to cope with this low SNR is generalized canonical correlation analysis. I am Simon Gerenaert, and I will present our newest work on a stimulus-informed generalized canonical correlation analysis technique for stimulus following brain responses. Generalized canonical correlation analysis, or GCCA, is a powerful EEG signal processing tool when you have multiple views of the same data. For example, you have several participants, several subjects that are attending the same audiovisual stimulus as in this image. The objective of GCCA is then to find these neural decoders per individual subject that extract correlated components among these different subjects, among these different EEG signals. In other words, they try to transform the original EEG signals in such a way that the outputs are, for example, pairwise maximally correlated. And this can be quantified through the intersubject correlation. As such, GCCA can be used to, for example, quantify the intersubject correlation, to quantify how much these EEG signals are related or correlated to one another, which can be used as a proxy for example, attention or engagement, as in the work of Lucas Parra. By definition, the only correlated activity that can happen between these different EEGs when these different subjects are attending to the same stimulus is related to the stimulus. Therefore, if we can quantify this intersubject correlation and find significant correlations, it's very clear that you have something related to attention or engagement and so on. Secondly, it can be used as a dimensionality reduction technique to reduce the dimensionality of this original high-dimensional EEG sensor space to a lower dimensional hidden subspace, which only contains the relevant activity. That is the activity that is correlated between these different EEGs. And thirdly, it can be used to summarize a set of EEG recordings to find a common shared subspace that summarizes these different correlated components. One of the main advantages of GCCA is that it is stimulus unaware. That is, that it does not require any information about the stimulus to be able to extract these correlated components. However, this strength can be at the same time a disadvantage. As said before, one of the main challenges when using natural stimuli in these natural brain-computer interfaces is the extremely low signal-to-noise ratio of the stimulus following neural response. Therefore, if the stimulus is available, why don't we use this stimulus as side information to improve the estimation of these neural decoders and therefore extract more robust correlated components? Therefore, the objective in our work is to use the stimulus here as side information to steer and improve the estimation of these neural decoders and therefore to find higher intersubject correlations by stripping or dealing better with all the noise that is present in these EEG signals. There exist several implementations of the GCCA objective. Here we choose for the MaxFAR implementation because it conveniently allows to find these neural decoders from a generalized eigenvalue decomposition. Say that we have these k different EEG signals, x1 to xk, of these subjects attending to the same stimulus. We now want to find these neural decoders wk such that their output signals xk, wk are pairwise maximally correlated. To see how this can be solved as a generalized eigenvalue decomposition, we reformulated this problem as follows. We try to find the shared subspace F that is on average closest to these transformed EEG signals. So the sum of the squared errors between the transformed individual EEG signals and this hidden subspace needs to be minimal under this orthogonality constraint. And as we show in our paper, this can be solved as a generalized eigenvalue decomposition of the matrix pencil R dxx Rx, where Rxx is the correlation matrix of the concatenated EEG signals, and R dxx is a block diagonal matrix with on the diagonal the individual autocorrelation matrices of the individual subjects. Now we want to go to this stimulus-informed GCCA technique, where we use the stimulus information as side information to improve the estimation of the neural decoders. However, we want to retain this attractive property of the MaxFAR formulation, where our solution boils down to a GEVD. In other words, we are looking here for these neural decoders WK again, which applied to the XK EEG signals give rise to XKWK. Now the stimulus is represented by this Y. This can be any feature of your video footage or your speech or whatever. At the same time, now we want to look for the stimulus encoder V, such that the encoded signal YV is also pairwise maximally correlated with the transformed EEG signals. In other words, we just look at the stimulus as an extra view of the same data, or quote unquote, as an additional subject, which leads to the following formulation. Here we again have the GCCA optimization problem, but now with one extra term. This term represents the stimulus. We have our encoded stimulus, which is now also pulling, which also needs to be close to this hidden subspace S. The amount at which it pulls on this hidden subspace is controlled by the hyperparameter rho. If rho is very high, our hidden subspace needs to be very close to the encoded stimulus and vice versa. From another perspective, you can look at this term as a task-informed regularization method, as an intelligent way of regularizing your problem, of injecting a priori or contextual information to improve the estimation of these neural decoders and of the hidden subspace S. In the paper, we now show that this problem can again be solved by a generalized eigenvalue decomposition problem, albeit for some different variables. The solution we are looking for is for this W tilde, which is the appended neural decoders and the stimulus encoder on the data which consists of the appended EEG data matrices and again our stimulus representation. The matrix pencil of which we try to solve the GEVD is this RD X tilde, which is the block diagonal matrix with on the diagonal these autocorrelation matrices of the EEG, but also of your stimulus, and the right-hand matrix, which consists of this correlation matrix of, again, the EEG, but now also of the cross-correlation between the EEG and the stimulus representation, weighted by this factor rho. While this is not a symmetric matrix anymore, we can show that it still boils down to a real solution in terms of the eigenvectors and the eigenvalues. The most significant eigenvectors corresponding to high eigenvalues can then be taken to find the final neural decoders and stimulus encoder. To compare the original GCCA technique with our proposed stimulus-informed GCCA technique, we use a publicly available dataset of 19 subjects who are listening or attending to the same speech signal, the same story, and of which the EEG signals are available. Performance is quantified using the inter-subject correlation, which is defined as the average pairwise correlation between the transformed EEG signals. For the stimulus-informed counterpart, during training, we make use of the stimulus information via the stimulus encoder. However, again, during performance evaluation, we do not take the stimulus into account. Intersubject correlation is only quantified between the transformed EEG signals without looking at the stimulus. As such, we can compare GCCA and SIGCCA on the same basis. We perform two experiments. In the first one, we limit the amount of training data that is available per subject, from 45 minutes of training data until 1 minute of training data. On the y-axis, the intersubject correlations, which are very low, albeit significant, can be found. For 45 minutes, there is no difference. However, when we then start reducing the amount of training data, SIGCCA clearly outperforms GCCA, which we also confirmed via a statistical test using a linear mixed effect model. For GCCA, you need at least 8 minutes of training data to have a significant intersubject correlation, while already with 3 minutes, you can obtain this for the stimulus-informed counterpart. So the stimulus regularization here clearly does the job. In the second experiment, we reduce the group size from the full 19 subjects up to only quantifying the intersubject correlation between 2 subjects. For all group sizes, SIGCCA outperforms GCCA. Note that the significance level here decreases if you go to bigger group sizes. This is because the bigger the group size, the lower the chance that you will have a spurious intersubject correlation. For GCCA, you need at least 6 subjects to have a significant intersubject correlation, while already from 3 to 4 subjects, you can obtain this with the stimulus-informed counterpart. To sum up, in this work, we developed a new stimulus-informed generalized canonical correlation analysis technique that allows you to take the stimulus into account when estimating these correlated activity or components among the EEGs of subjects attending to the same natural stimulus. We did this while keeping the attractive properties of the Maxwell formulation into account, namely that it can be solved as a generalized eigenvalue decomposition. Our experiments show that it is superior with respect to the original GCCA technique, especially when you go to lower amounts of training data or smaller group sizes, which is important, for example, in time-adaptive decom. All our code, both for SIGCCA estimation and for all experiments, is publicly available online. The developed technique can now be used into various neuroengineering and brain-computer interface applications, such as in hearing devices or educational neuroscience, where you want to do group decoding and where also the stimulus information is available.